Welcome to Section 2, Computer Vision. In general, computer vision refers to methods for acquiring, processing, and understanding digital images. In this section, we will focus on image classification, the task of determining which label to assign to a given image. We will begin by providing an overview of convolutional neural networks, which are the main neural network architecture for computer vision tasks. Then we will dive into the nitty-gritty details of preparing images for consumption by neural networks, as well as two techniques found in most computer vision models called pooling and batch normalization. Finally, we'll combine what we've learned to build, train, and evaluate a CNN on the CFAR10 dataset, a popular dataset for image classification. Along the way, we'll also learn how to use TensorFlow's estimator and dataset utilities, which will help us build some of these more complex models in much less time. But today is all about convolutional neural networks, or CNNs for short. Nearly all neural network-based models in computer vision contain one or more convolutional layers, so it will be essential to thoroughly understand them. First, we'll provide a brief definition of the image recognition task. Then, we'll dive into the intuition, graphical representation, and mathematics for understanding what convolution means. In this section, our ultimate goal will be to train a model to perform image classification. In this setting, our training data consists of images and their associated label. The set of all possible labels is defined by the set of unique labels in the training set. As seen in the example on the slide, we could have a training set of bird images, each labeled by the species of the bird. You may recognize that this is a supervised learning task, which we introduced in Section 1.2 on Machine Learning Basics. You may be wondering how we feed a picture of a bird as input to a neural network. Digital images are typically represented by a grid of pixels. For grayscale images, each pixel could be an 8-bit integer denoting the relative lightness or darkness of that pixel. And for color images, a common pixel representation is RGB, red, green, blue. That means that if we could zoom in on a single pixel, we could see that it was made up of 3 channels, one for each of red, green, and blue. We may have an 8-bit integer for each color, representing the relative amount of the color for that pixel. Okay, so now we know that we can represent an image as a 2-dimensional grid of pixels, each of which consists of 3 channels denoting the relative amount of red, green, and blue. Convolutional layers offer a clever way for transforming this grid-like image representation into collections of weights that learn different types of features present in the image. Let's see what that might look like. To get our minds in the right space, let's recall some distinguishing characteristics of fully connected, also called dense, layers, which we learned about in Section 1. Notice how every output neuron colored in green has a connection to every input neuron colored in blue. Furthermore, notice how we don't allow any shared connections between the two. By shared, I mean that we don't constrain any 2 connections or edges to have the same value at all times. Does it have to be this way? Of course not. What's less obvious, however, is what might be a useful alternative. Spoiler alert, convolution. First, I'll illustrate a very simple one-dimensional illustration of convolution. Next, we'll move to the 2-dimensional case of a rectangular grid. Also note that right now we are just getting a general feel for convolutions. Afterwards, we'll provide the more rigorous definitions and formulas to remove any ambiguities. As I hinted at in the previous slide, convolutional layers do not require each output neuron to have connections to all input neurons. In fact, we'll usually have each output neuron connected to only a very tiny region of input neurons. Another way of saying this is that they are sparsely connected. The next distinction we hinted at was the notion of shared connections. Note that I'll be using the term weights, connections, and parameters interchangeably, as is often done. Understanding shared connections is easier shown than said, so let's see what I mean. Here we see one output neuron connected to just the first 2 input neurons. I'm explicitly drawing the 2 connections differently, one with a dark dotted line and the other with a lighter solid line, to note that they are different. These 2 connections can change independently from one another, exactly the same as if they were in a dense layer. But what about the next output neuron? Now we see a pattern start to emerge. The neuron has 2 connections to the input neurons, but now the connections go to the second and third neurons instead of the first and second. In such a case, we say that we are sliding a window of size 2 along the inputs and with a step size of 1. By step size, I'm referring to the fact that we shifted over by 1 neuron when moving our window of size 2. The next thing you should notice is that these arrows look like the same ones connected to the other output neuron. That's because they are. The dotted line is an exact clone of the first dotted line, and both dotted lines are constrained to always have the same value. This is what we mean by saying parameter sharing. You'll also hear people refer to this concept as tied weights because the weights values are tied together. What do you think the next output neuron and its connections will look like? It should be no surprise that it has 2 connections, one to the third input neuron and one to the fourth input neuron. And again, these two connections are identical to the connection pair for any other output neurons. The pattern continues as expected for the remaining output neurons. Now we can tackle the two-dimensional case where our input is a matrix or grid of neurons, as is the case with images. We will now also begin referring to the small set of shared connections collectively as the kernel. In the last slide, our kernel was the set of two connections shared between all the output neurons. For the 2D case, we will follow the standard illustration practice of showing the kernel as a set of circles too. To be clear, these are just directed weighted connections from input to output, same as before. It's just less clear to have grids of arrows, unfortunately. Just as we slid our two-connection kernel along the last slide, let's see how that looks for our two-dimensional kernel consisting of 4 weighted connections total. Again, for each step of the kernel, we have one output neuron and vice versa. Typically, this is because we take the dot product of the kernel weights with the input neurons in the same manner as we did in the one-dimensional case. Since we are doing strides of 1, we slide our window by one step along the inputs and take the dot product of the new region to get the next output neuron. We continue this process left to right and top to bottom until we have the full output grid. Now I'll skip the rest of those. Note that in practice we don't actually do these sequentially, but rather all at once to take advantage of parallel computation, often with a GPU. You won't have to worry about the inner details of how that works though. TensorFlow makes this very convenient for us. So in the next slide we're going to go over the defining equation for convolution, but we'll need to cover some terminology first. As mentioned in the last slide, we will refer to the tensor of shared parameters as the kernel, also sometimes called the filter by TensorFlow. Recall how we slid the kernel in steps size of 1 along the inputs in the previous slide? In jargon speak, we'd say that we are using a stride of 1. We could also choose a stride of 2 here, like so. Well, what if we want a particular output size that can't be obtained with either a stride of 1 or 2 here? For example, what if we wanted our output shape to be a 3x3 grid? Most commonly, we'll use a technique called padding. Padding is the general practice of inserting dummy nodes around your inputs, and the most common form of padding shown here is zero padding. Notice how we can use a stride of 1 along the padding inputs to achieve a 3x3 output shape. With our new terminology in hand, we are ready for the last slide in understanding convolution, the math. Since this is a TensorFlow course, I'll use the same equation found in their documentation for the conv2D function, except I've added some colors and simplified it a bit to improve clarity. We've seen some illustrations of how the output neurons are computed given the input grid in a kernel. Although this may look complicated at first glance, it's really just a dot product. Each term of the summation is just the value of input neurons multiplied by the value of the corresponding connection or edge in the kernel. These terms are taken over the overlapping input and kernel pairs as we've seen in previous slides and summed together. In other words, a dot product. The main other thing to notice is that the stride essentially just tells us which input node to start with, or the location of the upper left corner of the overlapping region with the kernel. One last technical note for the math purists out there is that this formula is technically not convolution, but rather cross-correlation. Anytime you hear someone mention convolution in machine learning, they are almost certainly referring to the cross-correlation. The only reason I mention that is because you will occasionally see documentation refer to the cross-correlation rather than the convolution, but in machine learning we use the two terms interchangeably, for better or for worse. As always, make sure to read the links here for an in-depth look at the topics covered today.